Hello. In this lecture, we will be talking about vectors. In our school, we would have studied about vectors. So, we will just quickly brush up some of those concepts and maybe introduce a few new concepts. Okay. So, let us look at vectors. The definition of scalars. So, scalars are the physical quantities. To represent them, if we just need the magnitude of the quantity, we call them scalars, and we have learnt about it long ago. So, scalars, some examples can be time, for example. We do not need to define a direction to represent time. Pressure is again a scalar quantity. Temperature is a scalar quantity. We do not need a direction to define temperature. Pressure, somebody might say that we need to say that the pressure acts on a surface normal to it, but by the very definition of it, pressure always acts normal to a surface. The formula for pressure is force per unit area. So, whatever area that we are considering or we are looking at pressure, the direction of pressure will be normal to that surface. So, pressure is again a scalar quantity. Now, coming to vector. So, of course, vector is a quantity that has magnitude as well as direction. So, some of the common examples for vectors is displacement in a particular direction, or the derivative of displacement. Velocity and derivative of velocity, acceleration, force. Again, to represent force, we need the magnitude of force and in which direction does the force act. So, they are all examples of vectors. Now, in fluid mechanics, because we are generally concerned with the velocity of the fluid, the force is acting on a fluid, or the force is acting on a body because of the fluid. So, we need to analyze vector quantities often, and that is the reason that we are looking at vectors here. So, vectors can be generally represented with an arrow over them, or when we type it, we can also type vectors as a bold. So, it is convenient because we do not need to put an arrow every time we type the vector. So, in this course, predominantly I will try to use vectors as bold letters, but in some cases you might see a mix up, and you might see that vectors have an arrow over them. Okay. So, vectors, because we are representing its direction, and in space we can decompose it into three normal components. So, in general, what we will be looking at in this course in the Cartesian coordinate system. So, x, y and z directions, we can have the components of vectors. We can also have the components of vector in cylindrical coordinate system, where we have r direction, which is radial direction, angular direction, which is theta direction, and the axial direction, which you can say z direction or x direction. So, r theta x or r theta z coordinates are cylindrical coordinates, and then for some problems it is convenient to use spherical coordinate system, where we have one angular direction, one radial direction, which is r, and two angular directions theta and phi. Okay. So, in this lecture we will be talking about Cartesian coordinate system. However, as we go along and when we need to use cylindrical coordinate system, we will discuss cylindrical coordinate system. In this course, we will not talk about spherical coordinate system. Now, if we take the unit vectors along the three directions as E1, E2, E3. So, the three orthogonal directions, they can be x, y, z or r theta z. then we can write the velocity components as v is equal to v1 e1 v2 e2 plus v1 e1 plus v2 e2 plus v3 e3, where v1 is the component along direction 1 or along the direction e1, v2 is the component along direction 2 e2, and v3 is the component along the direction 3. Now, this can also be written in the summation form. So, this looks a bit intimidating, where we write v is equal to summation I is equal to 1 to 3 v I e I, where I can go from 1 to 3. So, if we expand it, we will get this. If we substitute I is equal to 1, so first term will be v 1 e 1, that is what we have here. The second term I is equal to 2 v 2 e 2, and then I is equal to 3 v 3 e 3. In certain cases, it is easier to represent this in terms of summations. So, we need to be familiar with the notations in summations. However, in this course, I will try to use as much as possible the expanded form of the vectors. Okay. So, if we take Cartesian coordinate system, so Cartesian coordinate system means in x, y and z directions. So, 1 is x, 2 is y and 3 is z. So, this vector can be represented as v x I v y j plus v z k. We are familiar with these notations I, j and k. They are unit vectors along directions x, y and z. In some books, you might find these directions being represented as e x, e y, e z. So, when talking about Cartesian coordinate system, we will use the notations I, j and k for unit vectors along x, y and z directions. Okay. So, the magnitude of vector a vector v which have component v x, v y and v z along x, y and z directions, we can obtain its magnitude by summing up the squares of the three components and taking its square root. So, the magnitude which is represented by 2 bars around the vector, that is equal to square root of v x square plus v y square plus v z square. Okay. Now, there is another quantity which you might have heard of, is called tensor. So, tensor is a generalization of that. If we take a quantity or if we take a system in which all scalars, vectors as well as other quantities can be taken into, where we need to have more than one direction to define a particular quantity. For example, when we talk about stresses, as we will discuss in later classes, that to define a stress, we need the direction or the surface on which the stress is acting and the direction in which the stress is acting. So, we need to define the stress components or to define the stresses, we need to tell two directions, the direction or normal to the surface on which the force acts and the direction along which the force acts. So, tensor is defined a generalized quantity, generalizing concept of vector, where we might need to have more than one information. So, you can relate it with say array what we use in programming multidimensional arrays. Now, scalar, so we can say the scalar is a tensor of order 0, where we have only magnitude and no direction. So, it has only one component. To represent a scalar, we need just one component. But for vectors, we need it has one direction. So, we have three components for vectors. So, it has magnitude plus one direction. Now, second order tensor, and that is why we are introducing the term tensor, because some of the quantities which we deal in fluid mechanics, for example, stress, momentum flux, velocity gradient, they are second order tensors. So, to represent them, we not only need the magnitude, but we need two directions to represent them, because if you have two directions, so x, y and z component to represent direction of one thing, and x, y, z component represent the direction of another. So, for example, when we talk about stress, we are talking about the direction normal to the surface on which the stress is acting or on which the force is acting, and the direction of force itself. So, we have three in three way, or we can have three components of the area vector, and we can have three components of the force. So, we will have 3 multiplied by 3, 9 components of a stress. Similarly, when we talk about velocity gradient, velocity will have 3 components, v x, v y, v z, and it can have variations along x direction. Each component can have variation along x direction, along y direction, along z direction. So, v x will be where we have component del v x over del x, del v x over del y, del v x over del z. So, similarly, if we have for 3 components, 3 multiplied by 3, 9 components. So, this is tensor of order 2, and to represent tensor, we need to define 2 directions. So, for example, when we write about tensor, it will be stress tensor, that will be tau I j in general term. So, there will be 2 directions, tau I and tau j, but when we talk about it in detail, then we will say which of this I represent the direction normal to the surface, and which of the symbol represent the direction of the force acting on it. Okay. So, then some usual stuff that we are already familiar with, that when we operate on vectors, so the normal operations which we have subtraction and addition, it is very common, and by now if we would have we have been doing mathematics, this would have been these concepts would have been built up in our subconscious mind. So, to just to repeat it, that 2 vectors can be added or subtracted by adding or subtracting their corresponding components. So, if you have vector, say vector A is equal to a1 I plus a2 j plus a3 k, vector B is equal to b1 I plus b2 j plus b3 k, and A plus B will be equal to a1 plus b1 I plus a2 plus b2 j, and the third component along the z direction will be a3 plus b3. Okay. Similarly, the same thing can be used for subtraction. Now, when we multiply a vector with a scalar, so if you have a, let us say a vector A, and this is multiplied by a scalar 3. So, what you will have, that 3 is multiplied by, let us say a1 I plus a2 j plus a3 k. Now, when you multiply with the scalar, you can just write 3 a1 I plus 3 a2 j plus 3 a3 k. Now, that is what we will have here, that each component is multiplied with the scalar. So, 3 is the scalar here. Of course, when you multiply the scalar with a vector, the direction of the vector is not changed, but a scalar can have a positive or negative sign, and as a result the direction of the vector might be reversed if you multiplied it with a scalar which has a negative magnitude. Now, if you want to differentiate a vector with respect to a single variable, for example, with respect to say time, this single variable time. So, when you differentiate a vector, you can differentiate each component of the vector and you will get the differential or the derivative of the vector. So, the next operation is product. So, when we talk about product, we can have actually 3 different operations on vectors. So, we can have that when you multiply 2 vectors, you get a scalar quantity. When you multiply 2 vectors, you get a vector quantity, and when you multiply 2 vectors, you get a tensor of second order. So, when you multiply 2 vectors and you get a scalar, that is called dot product. So, A dot B, where A and B are 2 vectors, A dot B is their dot product. So, dot represent, and that is the reason we call it dot product, and it's also called scalar product because the quantity that we get as a result of their multiplication, we get a scalar quantity. So, that is equal to A B cos theta. So, where here these A and B represent the magnitude of vector A, magnitude of vector B multiplied by cos theta, where theta is the angle between 2 vectors. So, the result of course is a scalar. Now, if we look at this, we can see that if you have a vector A and another vector B here, and the angle between them is theta. So, you can see that B cos theta, which is this component or this part, is the projection of vector B on vector A. So, you can treat dot product as a multiplication of magnitude of vector A multiplied by the projection of vector B on vector A, or you can do the other way around. You can write it as well, this is equal to B A cos theta. So, you can say that the dot product is equal to magnitude of vector B multiplied by the projection of vector A on vector B. Okay. So, this will also tell you that if you have a doubt that what is the angle between 2. So, you can take angle theta. If you take angle 2 pi minus theta, that will also give cos 2 pi minus theta is equal to cos theta. So, that will give you the same answer basically. So, if you have mutually perpendicular unit vectors, when we talk about the components, we can have components I, j, k unit vectors or unit vectors E r, E theta, E z in cylindrical coordinate system. So, if we write in general that there are 3 perpendicular unit vectors E 1, E 2, E 3. So, if you have perpendicular vectors, then that means theta, when theta is equal to pi by 2, we can see from this that cos theta is equal to cos pi by 2 is equal to 0. So, A dot will be 0. So, if a vector is multiplied by itself, then the angle, so unit vector E 1 dot E 1, the angle between them is 0. So, that will be the product is 1. E 2 dot E 1, the angle is 90 degrees, so it's 0. E 3 dot E 1 is equal to 0. Similarly, you can have other combinations of these. So, when a unit vector is multiplied by itself, the dot product is 1, and when it is multiplied by other unit components, of course, we are talking about 3 perpendicular unit vectors. So, then in these cases their dot product is 0. Now, for specific, if we take E 1 is equal to I, E 2 is equal to j and E 3 is equal to k, of course, again we will have I is equal to 1, j is equal to 1, k is equal to 1, and other products when I dot j or I dot k they are equal to 0. So, the other thing that we have already noticed here, that we either take A dot B or B dot A, they are equal. Now, when we take two vectors and multiply it, and if the result is a vector, then what we call it, cross product. So, the symbol here is, we use a cross here. So, A cross B is equal to magnitude of vector A, magnitude of vector B sin theta into a unit vector E A B, which will be normal to this, normal to both the vectors. So, you have a plane in which both the vector will be there, and this vector E A B will be pointing normal to it. So, this product is a vector, and then of course, it will be normal to it, but which direction, because you can have two directions. So, right hand thumb rule comes here, that if the fingers of right hand are curled from vector A towards vector V, then the resultant vector or the unit vector, it will point in the direction of thumb. So, when you go from A to B, it will be pointing in this direction. So, A cross B will be normal to board, or B cross A will be entering or inside the board. This will be pointing inside the board if we take B cross A, and A cross B will be pointing away from the board. So, that also tell us that A cross B and B cross A are not equal, because their magnitude are equal, but their direction, they are different. Okay. So, that is cross product. Now, if we take in terms of unit vectors that we write, generally when we work with vectors, we will be writing all the vectors in terms of its components. So, it is important to understand or important to know and remember the cross product of unit vectors of these x, y, z direction or r theta z direction. So, again E1 cross E1, because when sin 0 is equal to 0. So, E1 cross E1 will be equal to 0, E2 cross E1 is equal to minus E3, E1 cross E2 will be, as we see here, E1 cross E2 will be E3. Again, when you multiply or when you have a cross product of a vector with itself, you will get the result is 0. If you multiply two vectors, two unit vectors, you will get the third one, and the direction will depend, it may come with plus sign or minus sign. So, you can see that if you write E1, E2 and E3. So, when you have E1 cross E2, you will get E3. If you take E2 cross E1, you will get minus E3. If you take E3 cross E1, then you will get E2. If you take E2 cross E3, what you will get? E2 cross E3, you will get minus E1. Okay. So, if you have vectors A1I plus A2j plus A3k and B1I plus B2j plus B3k, then their cross product can be written in terms of a matrix, where the first row is the unit vectors I, j and k. The second row is the magnitude of the first vector A. So, A1, the components of first vector A1, A2 and A3, and the third row will be components of the second vector B1, B2, B3. So, when we simplify this, we can write I multiplication of, so A2 B3 minus A3 B2. So, that is first component minus j a1 b3 minus a3 b1. The third term will be plus k multiplied by a1 b2 minus a2 b1. Okay. So, if we want to have the sign for all the terms as plus, so we can change the order of these terms, that will be when it goes inside, then it becomes a3 b1 minus a1 b3. Okay. So, that is about cost product. Now, the third operation which you might have not been familiar with is that if you can also take a dyad product. So, when you multiply two vectors and you get a second order tensor, then it is called a dyad product. So, if you have a vector a1 I plus a2 j plus a3 k and another vector b1 I plus b2 j plus b3 k, you can take its dyad product, and this is the symbol. So, when you see this symbol a cross under a inside a circle, then you know that it is a dyad product, that when you multiply these vectors you get a tensor, and the magnitude of this tensor will be a1 b1 a1 b2. So, this is the matrix that you get by the multiplication of this tensor. Okay. So, the other operations or other operation that we will be interested in is differential operation on vectors. So, in Cartesian coordinate we define a operator which is del is equal to I del by del x plus j del by del y plus k del by del z. So, as you will notice that this looks like a vector or del operator, it is also called nabla. So, you might notice that this symbol the inverted triangle or triangle upside down, we call it del, and this symbol is also, I generally keep pronouncing it del. So, because of habit I use del for both, but you can also, to differentiate between the two, you can also pronounce this symbol as do. Okay. It can be pronounced as do or del, and sometimes people also called it curl d. Okay. So, this is, as you can see, that there are three components I, j and k. So, this appears to in along the x direction, y direction and z direction, there are three components, but we will have these differential operator del by del x, del by del y, del by del z. So, this operator does not stand or does not hold good or does not mean anything alone, but when it is operated we get a vector if we operate on a scalar, as we will see. So, this is a vector operator, it has components along the three directions, but it cannot stand alone. Okay. So, we can operate it on a scalar, we can operate it on a vector, or we can operate it on a tensor, and that is what we will see. So, the other thing that I would like you to notice here, that I have written these components or I, j and k just before the derivatives. You can also write this after the derivatives, but you need to remember the fact that these unit vectors are not being differentiated here. So, del by del x is not del by del x of I. Okay. It is I multiplied by del x, j multiplied by del by del y plus k multiplied by del y. Okay. So, if we operate the del operator on a scalar, let us say this scalar is f. So, if you operate it on a scalar f, what you will get is x component is I del f by del x, the y component will be del f by del y, and the z component will be del f by del z. So, what you have done when you operated del operator on a scalar, you get a vector. Okay. So, if you talk in terms of tensor, when you have a gradient operator or when you operate it in terms of gradient, the order of the tensor is increased by 1. A scalar becomes a vector, and you operate on a vector, the vector becomes a tensor. So, when you take the gradient of a vector, you remember that velocity gradient, I said that the velocity gradient is a second order tensor. So, let us look at a simple example, that if we say, or if we have a function f is equal to, or a scalar function which is x square plus y square plus z square, and we need to find its gradient. So, del f by del x. So, del by del x is partial derivative of f with respect to x. So, we can treat when we are taking partial derivative with respect to x, we can treat, or we need to treat y square and z square as constant. So, del by del x of f will be 2x. So, the x component will be 2xi, the y component similarly will become 2yj, and the z component will be 2zk. So, the gradient of x square plus y square plus z square scalar will be 2xi plus 2yj plus 2zk. Now, the second thing is divergence. So, divergence, when we operate the del operator on a vector in terms of dot product. So, when we take the dot product of del operator with a vector, we get its divergence. So, del operator we know that is in Cartesian coordinate system, I del by del x plus j del by del y plus k del by del z. Okay. We take its dot product with a vector v x I plus v y j plus v z k, and because it is a dot product. So, only the component where the vector it is multiplying, or the unit vectors are multiplying with itself, they will be non-zero, other terms will become 0. So, you will have del v x over del x plus del v y over del y plus del v z over del z. Okay. So, that is the divergence. So, as we can see here, when you take the divergence of a vector and it is a dot product. So, when you operate it on a vector, what you get is a scalar quantity. So, divergence of a vector becomes a scalar. So, its order decreases by 1. If we write it in summation form, you will see that del dot v is equal to sigma I del v I over del x I, where I is equal to 1 to 3. So, if we expand it, del v 1 over del x 1 plus del v 2 over del x 2 plus del v 3 over del x 3, or if we write x 1, x 2, x 3 in terms of x, y and z, then we can have a del v x over del x plus del v y over del y plus del v z over del z. So, summation is just a that you can write it in a compact form. Okay. So, again let us take a simple example where we need to find the divergence of a vector v, which is x I plus y j plus z k. Okay. So, if we take its divergence, we can write I del by del x plus j del by del y plus k del by del z dot the vector v, which is x I plus y j plus z k. So, when we solve it, del by del x by del x. So, differentiation of x with respect to x, you will get 1, differentiation of y with respect to y, you will get again 1, and differentiation of z with respect to z, you get 1. So, you add these 3 and you will get 3. So, del dot v in this case will be 3. Now, so we have looked at that what happens when the del operator is operated on a scalar quantity and we get a vector and which is called gradient. When the del operator is operated on a vector and we take the dot product, we get divergence. When we operate the del operator on a vector and we get a cross product, then we call it curl. So, cross product of del operator with a vector is called curl. So, del cross v, by the definition of cross product, we can write this in matrix form. The first row will be I j k, the second row will be del by del x, del by del y, del by del z, all three are components of the first vector del. And the last row will be v x, v y, v z, which are components of vector v. So, when you simplify it or when you write it in the expanded form, what you will get is the first term will be I del v z over del y minus del v y over del z plus j del v x over del z minus del v z over del x plus k del v y over del x minus del v x over del y. Now, again let us do an example to find the curl of a vector v, where it is v is equal to x square y square k, the other two components along x and y directions they are 0. So, if we find the curl of this vector, we will have the first term or the v x is 0, v y is equal to 0, and when we simplify it, we will get only two terms. So, 2 x square y I minus 2 x y square j will be the del cross v. So, we have looked at the dot product of a vector with the del operator, cross product of a vector with the del operator, and if we operate the del operator and take the dot product of del operator with a vector v, then what we get is gradient of a vector v. So, gradient of a vector v will be a tensor, and you can write this in the summation form easily. So, which will have again 9 components. You can have summation over I and summation over j, del v j over del x I, and e I e j is the direction. So, you can expand it and write all the 9 terms. So, this if v is the velocity vector, this is what we will have a velocity gradient term. Okay. So, velocity gradient is the dyad product of del operator and the velocity vector. Now, we can have another operator which you would have studied in mathematics already, which is called Laplacian operator. So, if you take a dot product of del operator by itself, then you will get a scalar operator which is del 2, which we pronounce. So, del dot del f, if we do, then we can write in the expanded form I del by del x plus j del by del y plus k del by del z dot I del by del x plus j del by del y plus k del by del z operated over f. So, when you take this dot product, you will get the non-zero terms where I dot I. So, del 2 by del x 2, del 2 by del y 2 plus del 2 by del z 2 operated on f, and when you substitute here, what you will get is del 2 f over del x 2, del 2 f over del y 2 plus del 2 f over del z 2. So, del 2 is equal to del dot del. So, that is equal to sigma I is equal to 1 to 3 del 2 over del x I 2. So, if you expand, you will get del 2 over del x 1 2 plus del 2 over del x 2 del x 2 2 plus del 2 over del x 3 2. Okay. So, you can write it in summation form. So, all of these operators we will later use when we write down the equations in the vector form. So, we will further discuss some of these things, but before we start the course I just wanted you to refresh your memory and remember some of these things and practice some problems. So, when you are looking at the derivations or when you are looking at the problems, you can appreciate it in a better manner. Especially we will be using curls, divergence and gradients quite frequently. So, we need to remember what these terms mean specifically. So, we will stop here. Thank you.